Hi, in our last lecture, we discussed about some uniform probability distributions, both for discrete and continuous variable cases. And in this lecture, I'll be discussing about two other important probability distributions. One is what we call binomial distribution, and the other one is the normal or Gaussian distribution. So before going to the binomial distribution, I must let you guys know that not all the time the outcome of a binary variable is equal. That means that they follow a uniform distribution. We have seen in our uniform distribution cases, especially for the binary case, that one popular example is tossing a fair coin, and it turn out to be that values for both tail and head are equal, but it's not always the case. For example, I am sure that in you guys work or in research, you try to answer some yes/no questions. Not necessarily in your research, but in our everyday life, we encounter some yes/no question. For example, is it going to rain tomorrow? And I just took a snapshot of today's weather. Today is Thursday. It's an Allendale weather from the Weather Network, and we found that Friday the chance of rain they are showing 1%. We are kind of near to surety that there will be no rain tomorrow, but we are not saying that the rain will be 0%. So there is a probability associated with any prediction. So this is a typical yes/no question, and if I ask, or if you ask yourself that am I going to get a grade A for this course, then the chance is not random, that it be the chance is not 50-50, because you know yourself that how you're doing, and you can predict that your grade will be based on like your preparation and your performance. It's not 0.5 yes or 0.5 no. So now I'll be showing you the binomial distribution. The idea of the binomial distribution is you repeat a binary experiment n times, and then you have to tell that how many times your results will be positive or negative. So it's a kind of repeated experiments distribution that the binomial distribution captures. So again, if you look at the x-axis, you will have the experiments that you're repeating, starting from 0 to the number of experiments you continue. So for example, if you look at the red graph here, so it is telling that, okay, I repeated my experiments, the binary experiment 40 times. Binomial distribution has two parameters. One is how many number of experiments you want to actually repeat. So that is what is represented with n. And there will be a probability of one of the outcomes. So for example, outcome of yes or outcome of no. So for example, for the red graph showing the case of a binary experiment with the probability of head yes is 0.5. So you can quickly connect that here we are talking about a uniform distribution case, but the green case is not the same, because we have a higher chance of getting a yes or true or head, whatever your experimental setup is. So let's go to the formulation. So if you look at the binomial distribution has two parameters: n, the number of experiments you want to repeat, and then probability of getting a truth for one of the outcomes, And what is your goal? Starting from 0 to n, what will be the chance distributed over the axis value, And there is a formulation for this. So you want to know that out of my n repetitions, what will be the probability of k? K meaning the value is starting from 0 all the way to n. And the formulation is you have n prime and divided by k prime times times n minus k prime. So this is what we call binomial distribution. And why? Because if you look at the graph, then you can quickly see that the values are not uniform, but they are following a certain pattern, And let's take the red graph as an example. So as you see that the probability is 50-50, and we are doing 40 times the experiments. So you can quickly come to the conclusion that the highest probability you will assign to the middle point. That meaning you are saying that if I repeat the coin testing experiment 40 times, then I have highest probability is I will get 20 coming to be head or tail. So this is all about binomial distribution. And again, binomial distribution is for a discrete variable with two possible outcomes. And we will repeat the experiments many times. Okay, so let's move to the next distribution we call normal distribution or Gaussian distribution. This is an example of a continuous variable distribution, or a measurement variable distribution. Some of the examples are, okay, we want to get a distribution of the height of the students of this class, or maybe the salary of a group of professionals with or similar background. So the normal or Gaussian distribution has two parameters. So this is the mean of the population or sample we are talking about, and there is the standard deviation. So if you have mean mu and standard deviation sigma, you will have a bell-shaped curve, just like just like all these three curves, and the curve will be centered at your mean. So that's the idea. If you look at the height and the width of these graphs are actually mainly described through their standard deviation. So if we compare this blue curve with the red curve, we can tell that if they represent two different samples of the same data, then the red distribution has more variance than the blue distribution. So let's look at the distribution formula itself. If you look at the first part of the equation, we have 1 upon the sigma, that is this standard deviation, multiplied by a scalar, that is the square root of 2 pi. And then you have an exponent function where you will have x. X is the values that you want to plug in as your input for the x-axis, and then mu is the mean of the sample and divided by 2 times the variance. So this is the formula. If you plug in, then you will get the continuous distribution of your variable. In the coming days, we will be working on some data, and we can explain the data using this distribution. And this is the way how we can estimate the probabilities of each data point within your data set and its corresponding probability if you are convinced that the data follows this particular distribution. So one point I forgot to mention in the case of binomial distribution, we have already learned the summation of all the possibilities is 1. This is one rule, what we call the rule of the probability mass function, and each probability value should be greater than or equal to 0. So no negative values for probabilities. And we have a similar rule for a continuous distribution, but the summation symbol is here replaced with the integral symbol. And I hope that you guys have some knowledge about calculus. If not, then just think that this is just a continuous summation. Another thing is that for continuous cases, we don't measure probability for one particular point. We always have a range of values associated with the probability. For example, here we are telling that the probability of x being between a and b is the summation of the probability function we are using here times the delta x. But again, you have to have calculus background to understand this clearly. So we have like some very nice properties that we should learn about the normal distribution. The distribution is symmetric. So for example, here the mean is 0, but you can see that the right side of the axis and the left side of the axis kind of symmetric to each other. Another point we mentioned that here the probability is the highest near to the mean. You can tell that the value points that are close to the mean, they occur more frequently. Some other metrics, we are saying that if certain data follows a normal distribution, then about 95% of the data, they occur, or maybe like they are found within 2 standard deviation around the mean. What I'm saying that, let's say if we think that the height of the students in this class follows a normal or a Gaussian distribution, then 95% of the students' height is within the 2 standard deviation of the population per sample. That's all for this part of the presentation. If you have any question, feel free to reach out to me and I will help you to clarify things. Thanks.